Let's continue. Next up, we have J.Luebsen with robustly safe data optimization.
Yeah, you can see that the title is actually a bit different. The title that you just mentioned is for the poster. Maybe I selected the wrong button there. Yes, so as mentioned already yesterday, today I talk about a safe Bayesian optimization algorithm for tuning the optical synchronization system at the European XFEL. Yes, so we are using it just to automatize some controller tuning, which was done previously by hand. So it's a heuristic method. And these are usually very tedious. So there exist mainly two different approaches. First is the model-based approach that we saw yesterday, where the dynamics of the plant is identified, for example, with a linear model or something like that. And the controller is tuned to this model. Clearly here, the accuracy depends on the fidelity of the model. So if a model is wrong or if our real plant is actually highly nonlinear, then our controller would perform bad. The second approach is to use an online tuning method where the controller is directly tuned. So this can be done if we have a predefined controller structure, for example, PID controllers, where we have just 3 tuning knobs that we can change and some costs that we want to optimize. Yeah, and this is what we propose in this talk. The plant that we are considering is the laser-based synchronization system at the European XFEL. The figure shows here now the main building blocks of the accelerator. So this yellow one here is the LINAC. And the synchronization system is denoted here below. It consists of lasers, so this master laser oscillator, and fibers. These are here the red lines. Then we have here the subsidiary laser oscillator, and we have here the second link and the pump probe laser. So the pump probe laser is used to initialize some chemical reaction, which are then in some kind photographed by the X-rays of the accelerator that come from here. And the quality of the observations depends on the timing gap that we have between this pump probe laser pulses and the X-rays. Since the European XFEL is the largest linear particle accelerator in the world, the machine time is very expensive. So we want to optimize the system as fast as possible. We can measure this gap with a device. It's called the photon arrival monitor. It's also still a prototype. And these measurements are what we saw very noisy. So our algorithm needs to be able to handle this. The third part is that the timing gap must be below some constant value t. Otherwise, if we exceed this value, an alarm system comes in and everything is unlocked. So nothing works anymore, and it needs some time to lock all the subsystems again. So we clearly want to avoid this. This characteristic is called safe in our this presentation. Mathematically, this problem can be described as the minimization of a cost function f of x, such that some constraint g of x are fulfilled. So g of x is denoted positive here if it's fulfilled. The special thing here is now that f as well as g are unknown a priori. So we need to learn them with our observations. And what we propose here is a black box approach. It is safe in the sense that we defined before. It learns a probabilistic surrogate model, so it's able to handle noisy measurements. And what we have seen in our benchmarks, it shows an increased convergence rate compared to other optimization approaches, so other Bayesian optimization approaches and other non-parametric or simplex approaches like NLW. Yes, so shortly about the contents, I will start with a short theory section where Gaussian processes, the model that we are using, and the algorithm itself are covered. The second section is then about the benchmarks. As you saw the figures already yesterday. And finally, a short conclusion and outlook about the future work. So the upper right figure here illustrates the flow chart of Bayesian optimization. And the red box illustrates the part which we are now considering on the slide. The black box model here represents the underlying plant, or rather the cost function that is going to be optimized. So our f of x. We can set here some inputs. So if you think about our plant, we have some controllers. So PI controllers in our lasers, links, which we want to tune. And these PI values are denoted by the X. So we can set these inputs and measure here the output Y. This Y is composed of the true function value, f of x, and some noise term. In our case, we assume it's Gaussian distributed. Then the input-output pairs are gathered in a set. So this is our training set, and are fed into a Gaussian process model. And this Gaussian process model gives us some predictive distribution, so consisting of a mean and the variance at specific points. Yes. So we have here an example function in the left figure, so just a quadratic one, and we have some observations. These are the blue points here. So we explicitly measure the function at the values here, -3, 0, 4, and 5. And the question is now, how would the predictive distribution look like? In the first instance, we need to do some assumption. That is that f can be represented by a Gaussian process. This Gaussian process is completely defined by a mean function. In this case, we selected it to 0, and a covariance function, or also called kernel. So this is the k here. And this kernel encodes some properties of our cost function, for example, smoothness. In order to guarantee that the function can be modeled by the Gaussian process, we assume that f of x is a member of the reproducible kernel Hilbert space defined by the kernel. So this is more for theoretical perspective. Since kernels like the squared exponential, that is denoted here, fulfills the universal approximation property, so it can model or can at least approximate a very wide range of functions. And this means that this assumption is not very restrictive. In addition, you can see here the kernel has two hyperparameters. So the sigma f, this is the signal variance, and the L, the length scale. And these hyperparameters can be adjusted. We will see later how this can be done. Now, using the law of total probability, the predictive distribution, as shown here in the right figure, can be calculated. So we can see here at our measured points, the blue stars, we know the function exactly, and if we increase the distance to these blue points, our uncertainty increases. So the gray area here. The last point in the flow chart is now the acquisition function, which searches for new promising inputs that are very likely to minimize our cost function. The next point that is going to be evaluated is defined as the argument of the maximum of this acquisition function. However, recall that a constrained optimization is considered here. This means not every arbitrarily x can be selected. So the question is now, how can this be addressed here? In our examples, we consider that our constraint function g to be an offset of our true target function f. Recall that safeness is defined just as the timing gap between X-rays and pump probe laser pulses need to be bounded by some threshold t. So we know the dependence between f and g explicitly, and therefore it is enough to use one Gaussian process to model both. However, if we don't know the dependence between f and g, we need two, but all the following statements can be adapted accordingly. First, similar to SafeOpt, we define three sets. So first, the safe set. This is includes all points where the safe conditions are fulfilled which is in this case just the upper border of the gray area, so our upper confidence bound. Then we have the minimizer set in red. This set includes all points that are very likely to improve the function. And last but not least, we have the expander set. So this is a set containing points that can expand our safe region. And here we just set them to the boundary of our safe set. In contrast to safe options, we divide our optimization procedure in two phases, namely exploration and exploitation. During the exploration phase, the algorithm tries to observe the reachable set, which consists of all points where the constraints are fulfilled. And the exploration is done by evaluating the expanders with the highest uncertainty repetitively. So you can see here now, we started with the right one. Now it tries to observe the safe region rightwards because the gray area here at the expander is larger than on the left-hand side. This is repeated sometimes until our uncertainty of the expanders falls below some threshold. And then the exploration phase is terminated. This marks now the initialization of exploitation, so where we want to optimize the performance. Now we are freezing the safe sets, and the hyperparameters are fitted, such that the negative log marginal likelihood is minimized. Then only new inputs from the minimizer set are selected, so only points that are in the safe set that we observed. And you can see here now, the fitting does not make a big difference here now because we selected the hyperparameters before quite good actually. And now here after 2 additional steps, the algorithm terminates because it found the global optimum. So evaluating Soleil expanders makes the exploration more efficient, as the reachable set is observed within the lowest number of observations. And exploitation, the information that we gathered is then used to fit the kernel to our data set, so to have the right complexity of our Gaussian process. And this provides a better predictive distribution, and then we can find the optimum faster. And all this together increases the convergence speed and finally decreases the required time that is used on the machine. As these sets that I just introduced, so the safe set, minimizer set, and expander set, need to be calculated numerically, we run into feasibility issues if the dimension of the space is too high. One approach to apply safe Bayesian optimization is on an iteratively changing subspace. So depending on the dimension of the subspace, we have, for example, line BO for one-dimensional subspaces. This means we optimizing just one parameter at the time. Or we have the plane BO where we optimize 2 parameters at the time. Yes, SY can be noisy, so our measurements. We need to take into account some robustness, which is in this case that we include the posterior mean that we have. Because when we switch our subspaces, we always take the best observation that we have. But the noise can, if it's too high, the noise maybe gives us some bad estimation of this. Yes, so now in the following, the performance of the proposed algorithm is compared. Here we have consider a subsystem, a system consisting of 5 subsystems arranged in the chain. So this is a simulation of the laser-based synchronization system. So you can see here, we have here PI controllers. So every PI controller has 2 tuning knobs, the K value and the I value. And we have 5 subsystems, so in total we have 10 tuning knobs. The inputs here W1 to Wn+1 are assumed to be white Gaussian noise. And our goal is to minimize the RMS norm of the performance output Z. Then there exists a theorem called Parseval theorem, which denotes that this can be expressed as a H2 minimization of the closed loop system. So what we are doing is we minimize the H2 norm, actually. Yes. So the entire optimization is then repeated for 10 times for different starting points. And the figure here now shows the cost over the number of required observations. The lines and the dashed lines denote here the mean cost of the optimizations, and the colored areas are the variance. So we can see that the line BO approaches converges faster and have a smaller variance. So for this application, so the line BOs are the better choice. Furthermore, we can see that our approach, the yellow one, converges approximately 50% faster than the safe one. We repeated the tuning procedure also on the real plant, now with only 2 subsystems, so 4 tuning knobs. Here the RMS norm is directly measured, but averaged over multiple samples to reduce the influence of the measurement noise. The performance is here now compared to the well-known Nelda-Mead. And as you can see in the lower figure, we have here now the time on the horizontal axis. Nelda-Mead is not able to find reliable, the optimal solution, what can be seen by means of the high variance that we have here, because the measurement noise is just too high, and Nelda-Mead cannot handle it. If we increase the number of RMS samples, the variance of the sample mean will decrease, but the time that is required for the optimization is significantly increased. So comparing the time of the upper figure and the lower figure, we can see that the line BO finds the solution approximately 4 times faster. Yes, so finally, to conclude the outcomes of this work, we were able to develop a sample-efficient and noise-robust Bayesian optimization procedure that shows an increased convergence rate compared to other methods. However, what is very important is that the safety guarantees that we used here are only applicable if we know the correct hyperparameters, which is in a real application not always, or rather seldom, the case. But I will address this problem in my poster. And yeah, about the outlook, there exist also some multitask Bayesian optimization procedures where you include some simulator samples. So it's not the true functions that you include here, but it is related to it. And you measure how large the correlation is. And also there, to guarantee safeness is not so straightforward, but also this is addressed in the paper. What you actually do is you calculate a posterior distribution of the higher parameters and calculate some interval where you have a lot of probability in, so some confidence, and then you need to scale your Gaussian process in the end. Yes, I thank you very much for your attention.
Time for one question.
So it's very interesting that your modified approach is actually faster than the safe one, because you explicitly separate the exploration and the exploitation phase. Can you elaborate more, like why would it be faster even if you first try to explore the whole space?
Yeah, so this comes from that we use the subspaces actually. And then, I mean, you need to find the minimum either. So you need to observe your subspace in this moment. And this is just the most efficient way to do it. And SafeOp just always picks the one with the highest uncertainty. And yeah, if you combine these first, observing this reachable set and then training it on this and then fix it just, makes it faster. So this is So it comes, the speed increase comes from these subspace optimizations, actually.
That means in your time estimation, it's the second part after exploration. It's all together
So
in your consideration of the time it takes.
yeah, it's all together.
It's okay.
All
Because
together.
I was-
Yes.